Hi there, welcome to a new video series. So this new set of videos is going to focus on the Fourier series, what it is, what its significance is, how do you write a Fourier series, and some applications of it. So before we get into all of that discussion, it's worthwhile just to remember why we generally do some kind of series expansions. So many people are familiar with the Taylor series. And with the Taylor series, what you actually do is that you take a function and you write it as an infinite sum of polynomials. For example, if you have the function f of x is equal to e to the power x, if you were to write out the Taylor series maybe around the point x is equal to 0, then what you would get is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So in our work, we often find that we're working with functions that are quite difficult to represent, and to simplify a lot of our analysis, we can express a function as the sum of a series. In this case, when you write the Taylor series near x is equal to 0, it's actually called the Maclaurin series. But anyway, so a disadvantage or a limitation of the Taylor series is that we cannot write Taylor series for functions that are discontinuous. So we can't actually represent discontinuous functions using the Taylor series. Can't represent discontinuous functions. So when we mean a discontinuous function, what we're talking about is something that looks like this, where we may have a function at a certain point and then it takes on some other values beyond a certain point. So this would be a discontinuous function. So this is where the Fourier series actually comes into place. So what we have noticed that we are able to do is that we can represent the functions as the sum of trigonometric terms. So we represent functions as sum or series of trigonometric terms. So that would be your sine and cos. So in these upcoming videos, we will actually show how we write this Fourier series for all these different functions. So that is not the focus of this video. This video is simply an introduction. So what does the Fourier series look like in general? So in future videos, we will see how we can write this Fourier series as for any function f of x being equal to a naught over 2 plus the infinite sum with a variable starting from 1 to infinity, and that variable being n. We have an, and we have cos times nx plus bn times sine of nx. So as I have just stated, the subject of future videos will be showing how to actually go about writing this for different kinds of periodic functions. So this is the key thing now. So we have to speak about periodic functions. We are primarily going to be writing all these Fourier series for periodic functions. So there is some bits of terminology that we need to be aware of. So what is a periodic function? So a periodic function is simply just where we have y values that repeat. They repeat themselves at regular intervals. Regular intervals. So the simplest example of this that most people would be familiar with is sinusoidal curves or sine curves. So if we take the function y is equal to sine x and we just do a simple plot of it, then we know that it starts off at 0, it goes up to a value of 1, goes back down to 0, goes to -1, and then it stops, and then it starts repeating itself. So we would know that it's actually equal to pi over 2, so that's 1, and that's -1, and it's 0 at pi, and it repeats this cycle every 360 degrees, which is 2 pi. So there's two important terms that we have to be aware of in our analysis moving forward. So the first one is the amplitude. The amplitude. So this is just the maximum y value. So we can see that the maximum y value is just 1, so that's what our amplitude is. So the answer to that is 1. The other one is the period. So what is the period of this graph? So the period is just the point at which the graph repeats itself. So we'll say when the graph repeats itself. So when would that actually happen? We can see that it completes its cycle at 360 degrees, and then after 360 degrees it just starts doing the same thing, and it just carries on like that. So the period of the graph is actually 360 degrees, or 2 pi radians. So we can now just write these two quantities, amplitude and period, for some kind of general sine function. So that is y is equal to 5 sine 2x. So if we plot this one out, and let's just say that's 2 pi. So what's going to happen is that we see the graph looking something like that, going back up there. So in this case, we see that it completes its first cycle at pi radians. So it's actually 2 cycles. There's 1 cycle, and there's 2 cycles within this 2 pi radians, or 360 degrees. So if we're looking at the period, so we have to check how many cycles are between 0 and 360 degrees. Zero degrees and 360 degrees. So in this case it's 2, and we can see that the period is just pi. So the amplitude, of course, is just 5. Okay, so that's 5. So now we can just generalize it a bit. So if we have the general form, we can write a general form as being y is equal to a sine nx. Then the amplitude is merely the value a, so it's that value a that's in front of the sine. And the period, how we determine that is we simply take 360 degrees and we divide it by this value n. Or we could also say 2 pi radians divided by n. So if we look at the previous example, we can see that the period was pi, and we got pi by taking this 2 pi and we divided it by this 2 here. So that's how we got pi. So the period in general is just were determined in that way. So the results that we have just shown now is the same for cos x as well. So if we have y is equal to a cos nx, then all of the above results are the same for this function as well. So just a little bit more terminology. So we have harmonics. So in general, f of x can be written as a different series of different sign components. So we'll say written as series of different sign components. So an illustration of this is we could have f of x equal to a1 sine x. We could have f of x equal to another value, a2 sine 2x. And we can carry on like that, equal to a3 sine 3x. So what's happening here is that we have these different numbers in front of the x. So it actually determines based upon this value of n. So this we would call the first harmonic, and that is the second harmonic, and that would be the third harmonic. So essentially it's the case that the value of n in front of the x determines what harmonic it is. So this first harmonic is also called the fundamental. So thus far we've looked at the sine graph as an illustration of a periodic function. So the question at this stage is, can we have functions that are periodic but not sinusoidal? So we're looking for functions that are periodic but not sinusoidal. We can find some simple illustrations of this. If we look at on the xy plane, we can have a function that's taking on the value 4. So that's taking on the value of 4, and it does this for 6 units of x. And then it takes on the value of 0 for 2 units of x. So at 8 units then, it's now going to take on the value of 4 again for another 6 units. So at 14 units, it's now going to drop back down to 0. And then 2 units later, at 16, it will again take on 4 units. So what we're seeing here is a periodic function, right? So let's look at what happened. So essentially, after 8 units, the function is repeating itself. So we have 4, that's what the y value is, and then we have 0 for 2 units, and then we carry on like that. So what would be the period of a graph like this? So the period is simply 8 units, because we can see that after 8 units, the graph is repeating in that same function. So we can actually write this analytically. So we can say that f of x is equal to 4 when x is between 0 and 6. So there's 0, there's 6, and y is taking on the value of 4. And f of x is therefore thereafter taking the value of 0 when x is between 6 and 8. So this function describes it, but we now need to make it a repeating function, a periodic function. So how do we do that? So we do that by just saying that f of x plus 8 is equal to f of x. So that means that x units plus 8, it's taking on this value of y. So remember that y, or rather f of x, is defined as we've just described it, and after every 8 repeating units, it takes on that value. So putting on this last line here, this last equation, that's what makes it a periodic function. So we can do one more example of this, of a periodic function, a repeating function that's not a sine curve. We can have a function that takes on the value of 2 as a straight line from 0 to 2. It takes on this value, and then it decreases to 5 like that, and then between 5 and 6 it takes on the value 0, and then it repeats itself. It carries on in that manner, right? So the first question is, what is the period? So the period is actually 6. We can see that the graph starts off with a straight line like that, and after 6 units we see it starts off with a strict line. Well, it's not exactly as I've drawn it, because I haven't drawn it the first and second segments exactly the same, but we can see that after 6 units it starts off with a straight line again. So the period is 6 units of x. So how would we describe this function analytically? So we have f of x that's equal to, so if we look at the first portion of the graph, we have a straight line between 0 and 2. So this portion of the graph corresponds to y is equal to x. So we just write x, so y is equal to x, and that's between 0 and 2. Then we have between 2 and 5. So x between 2 and 5. So we have another straight line. So how would you write that? We need to find the equation of this line. So that's minus 2 over 3x plus 10 over 3. So we get that by finding the equation of the straight line, which is fairly easy to do. So the gradient of the line is just 0 minus 2, basically y2 minus y1 over x2 minus x1. So that's y is 0 here and y is 2 here, so it's 0 minus 2, and the x values are 5 minus 2. So that gives us minus 2 over 3. And then we just find the intercept, so we just choose a value. We can choose this point here. So there y is equal to 0 and x is equal to 5. So the gradient is minus 2 over 3 times x, which is 5, plus c, the intercept, and the intercept is just 10 over 3. And then after we have this second straight line portion, we have a part of the graph where x is equal to 0. So we have to write that down as well. Sorry, y is equal to 0. And that is between 5 and 6. So if you write the function analytically for this repeating function, then that's what it's going to look like. But remember, we have to put in another line to actually say that it's a repeating function or a periodic function. So what we would need to write is that f at x plus 6, remember we have to bring in the period, x plus 6. So after every 6 units, we want to take on the value of f of x as we have defined it. So that's how we would write a periodic function for this kind of example. In the last video, we looked at periodic functions, what they are, how they are described, and we looked at the amplitude and the period of these periodic functions. And we saw that we write Fourier series primarily for periodic functions. So this video is going to focus on integrals of periodic functions. Specifically, we're going to write integrals for sine and cos, and they're going to contain integers m and n. And we're going to write these integrals over a single period. And what we have chosen as the boundaries is minus pi and pi. So the question is, why are we going to do this? Well, we need to do this because we get some important results that we need to use when we actually write out the Fourier series for different functions. So the first integral that we're going to look at is just the integral from minus pi to pi of dx, that's the constant. So if we integrate a constant, we'll just get x. And if we integrate from minus pi to pi, all we're just going to get is 2 pi. The second integral that we want to look at is the integral from minus pi to pi of sine nx dx. So you would remember that we just said we're going to look at all these integrals and they're going to contain these integers m and n. So these integers are quite important and we will see them in the upcoming videos, what role they play. So if we integrate this integral, it's fairly straightforward. The integral of sine is minus cos nx divided by n, and then integrating from minus pi to pi. So if we do that, we just substitute pi in. What we get is minus cos n pi divided by n plus, well, minus and minus, cos of minus n pi over n. And we would remember from our trig identities that cos of minus x is simply just equal to cos x. So once we substitute that identity in, what we get is cos minus cos n pi divided by n plus cos of n pi. Remember that this just becomes cos of n pi. So a minus and a plus just gives us 0. So that is the answer here. So the third integral that we're going to look at is simply cos. So we have integral from minus pi to pi of cos nx dx. So this is the third one. And that's just equal to the integral of cos is just sine. So we have sine nx divided by n. We're integrating from minus pi to pi. So when we substitute in pi, we get sine of n pi over n minus sine of minus n pi over n. And sine of pi is just equal to 0. So we have 0 here and we have 0 here. So the fourth integral that we want to look at is where we integrate from minus pi to pi of cos mx times cos of nx. So for this specific integral that we're looking at now, what we will say is that m is equal to n. So this is important. So if m is equal to n, then what this integral becomes is the integral from minus pi to pi of, we'll just replace m with n. So what we get is cos squared nx dx. So if we want to evaluate this integral, then we need to use an identity. And that identity is that cos of 2a is equal to 2 cos squared x minus 1. So we just solve for cos squared here. So if we do that, we get that cos squared a is equal to half cos 2a plus a half. Take the 1 to the other side. So now we can substitute that in. And when we do that, what we get is the integral from minus pi to pi of a half cos 2nx. So that's what the 2 is here. Plus a half. So this is fairly straightforward to integrate. So what we'll do is just bring in the half to the front. So integral of cos is sine. So we have sine 2nx, and we will divide by n, 2n, sorry. We just integrate 1, and that gives us x, integrating from minus pi to pi. So once we substitute in pi, we get half into sine of 2n pi divided by 2n plus pi. Then minus, substitute in minus pi here, sine of minus 2n pi divided by 2n and minus pi. So remember, it's going to be minus here, and so we have minus pi. So this just becomes plus pi, basically. So sine of 2 pi is 0, so that term becomes 0. This term is also 0. Sine of minus 2 pi is also 0. So then we have pi plus pi gives us 2 pi. Then 2 pi multiplied by a half just gives us pi. So what we have is that if we integrate cos mx times cos nx, where m is equal to n, what this gives us is pi. So the fifth integral that we'll be considering is the integral from minus pi to pi of sine mx times sine nx. So we'll also state here that m is equal to n. This is for a very specific case where these two constants are the same. So if that's the case, what we get is the integral of minus pi to pi of sine squared nx dx. So we evaluate this integral in the same way that we had done the last one. So what we need is the identity, trig identity, that cos 2a is equal to 1 minus 2 sine squared a. Solving for sine squared a, what we get is sine squared a is equal to a half plus half cos 2a. So putting this into the integral, what we get is the integral from minus pi to pi of a half plus half cos 2nx. So we integrate this in the same manner as we had done the last one. If we do that, integral of half is just half x. Integral of cos is sine. So we have sine 2nx divided by 4n. We have to divide by 2n here, and we multiply by this 2 here, so that gives us 4n. And we integrate from minus pi to pi. Substituting in those boundaries, we get half pi plus sine of 2n pi divided by 4n minus half into minus pi minus sine minus 2n pi, so that's a minus here. That's minus 2n pi divided by 4n. As was the case previously, sine of 2 pi is 0. So we have half pi plus half pi, which is just pi. Okay, so we can proceed. So the sixth integral that we're looking at is integral from minus pi to pi of cos mx times cos nx dx.
We had done this just now, but what we had said was m was equal to n. So now we are considering the case where m is not equal to n. So how do we evaluate this integral? So we need another identity, another trig identity, and that is 2 cos A cos B is equal to cos of A plus B plus cos of A minus B. And of course, we divide everything by 2. We have a half here and a half here. So putting that in, what we get is a half integral. Putting these terms inside, we get cos A plus B, so it's cos mx plus nx. So we'll just take out the x as a common factor. Okay, so we've taken out x as a common factor. We'll just write it in front. So it's cos m plus n x. So remember, this x is multiplied by what is inside this bracket. It's not being multiplied by cos. And then also in the same way, we have cos of m minus n x. All this integrated with respect to dx. So this is a straightforward integral to evaluate. What we get is a half. Integral of cos is sine. So we have sine m plus n, and we have to divide by m plus n. And the same is true of the other term. So we have sine m minus n divided by m minus n. Integrated from minus pi to pi. Substituting in pi and minus pi, we get a half into sine m plus n pi over m plus n, then plus sine of m minus n pi divided by m minus n. And it's essentially the same thing, but we'll just replace pi with minus pi. Okay, the first time we substitute minus pi, we get sine m plus n divided by m plus n minus pi, and the last term is also minus sine m minus n divided by m minus n and multiplied by minus pi. So all this is going to give us 0, right? Because sine of pi is 0 and sine of minus pi is equal to 0. So this entire thing is 0. So the seventh integral that we will look at is the integral minus pi to pi of sine mx times sine nx. And where we had previously considered m to be equal to n, we will now say that they are not equal. So if they're not equal, we need to use our trig identities once more. And the one that we shall use is that 2 sine A sine B is equal to cos of A minus B minus cos of A plus B. And of course, we can divide both sides by half. So substituting that in, what we get is the integral of half. You can write the half in front. cos of a minus b. So in the same way, it'll be cos of mx plus nx. So we'll take the x out as common factor. So what we have is cos m minus n x minus cos of m plus n x. And all this is integrated with respect to dx. So performing this integration, what we get is a half into cos, integral of cos is sine. So we have sine of m minus n divided by m minus n. And then minus integral of cos is sine once more. So we have m plus n divided by m plus n. And what we'll need to do, as was done previously, is substitute in pi and minus pi. So fairly straightforward to do. We get a half into sine of m minus n pi over m minus n minus sine of m plus n pi divided by m plus n. And now we substitute in minus pi. So, okay, so the next term will be negative. Sine m minus n minus pi divided by m minus n. And the last term is plus, a minus and a minus will give you a plus. So plus sine of m plus n minus pi divided by m plus n. And this entire thing is being integrated, sorry, it's already been substituted. So once more, sine of pi is equal to 0. So all of these terms become 0. Sine of minus pi is also 0. Okay, so the eighth integral that we're going to consider is the integral from minus pi to pi of cos mx times sine of mx. For this one, we need the identity that 2 cos a sine b is equal to sine of a plus b minus sine a minus b. And of course, we divide both sides by half. So substituting that into the integral, what we get is a half times the integral from minus pi to pi. And we have sine of m plus n x minus sine of m minus n x. So performing this integration, what we get is a half into minus cos m plus n x divided by m plus n plus integral of minus sign is cos, that's why we write a plus here. So we have cos of m minus n divided by m minus n. This is integrated from minus pi to pi. So substituting in pi, what we get is minus cos m plus n pi divided by m plus n plus cos of m minus n pi divided by m minus n. Then minus and a minus gives us a plus. The next term is plus cos of m plus n times minus pi divided by m plus n. And lastly, minus cos m minus n minus pi divided by m minus n. So we remember our previous identity that cos of minus x is just cos x. So if you look at that term and that term, you'll see that the only difference between them is we have minus pi here. And with this identity, we can see that they are the same. So that term is going to cancel out for that one. And it's the same for this one. So that term, second term will cancel with the fourth term. So this also gives us 0. So the final integral that we're going to look at, that's number 9. So the last integral that we're looking at is the integral minus pi to pi of cos mx times sine mx. For this one, we need the identity that sine 2a is equal to 2 sine a times cos a. Okay, and of course we'll divide both sides by 2. So once we substitute this into the integral, what we get is a half, and the integral of sine of 2a, so in this case it's 2mx. So this is fairly straightforward. So this is half, integral of sine is minus cos. So we have minus cos 2mx divided by 2m. So once we substitute in pi and minus pi, what we get is half into minus cos 2m pi then plus, because the minus and minus gives us a plus. So it's plus cos of minus 2m pi. So once again, we just remember that cos of minus x is just cos x. So it means that this term is essentially the same as that term. So they just cancel each other, minus and plus. So this term also gives us 0. So we've looked at 9 integrals involving various combinations of cos and sine and different integers m and n and all of these things. So what was the point of all of this? Why did we do all of these? Or how are these integrals going to help us in any way? So you would remember from the previous video, we had written what the Fourier series actually looked like. The Fourier series for any function, f of x, is simply equal to a naught over 2 plus the sum of some variable n, which starts from 1, goes away all the way to infinity of a to the power an cos nx plus bn sine nx. So how these integrals are going to help us is to find the values of an and bn. So these things are called Fourier constants. So that is going to be the subject of the next video. We will use these results, these integrals that we have just written down now, and use them to find these coefficients an and bn, these Fourier constants. Okay. In this video, we're now actually going to be writing out the Fourier series for a few functions, periodic functions that is. So if we just recall what the Fourier series actually is, it's f of x is equal to a naught over 2 plus an infinite sum of a variable n that starts from 1 and goes to infinity of an cos nx plus bn sine nx. So in order for us to be able to write out this Fourier series, we must be able to find these constants a naught, an, and bn. So there is a specific way in which these constants are determined. And in the last video, what we had done was that we had written out the integrals for a variety of different trigonometric functions. That's sine mx. We saw that this was equal to 0 for a period of 2 pi, with the bounds being from minus pi to pi. And we also had seen this for cos mx, also gave us 0. Then we saw when we take the integral of cos mx and cos nx, we get two different results. If m is equal to n, so if m is equal to n, then we just get cos squared nx or something like that. And if we evaluate that integral, we get pi. However, for every other value of m and n, which are not the same, so if m and n are different values, then this integral gives you 0. And then lastly, if we have, sorry, not lastly, so if we have sine mx and sine nx, and if m is equal to n, then we get pi. And if m is not equal to n, then we get 0. And then lastly, if we have cos mx and sine mx and we integrate this, then what we see that regardless of the values of m and n, if they are the same or not the same, it will give us 0. So these were the results that we had derived in the last video, where we looked at integrals of periodic functions. So if you want to remember how all these things came about, you can go and watch that video or rewatch it. So just another point to make. So these kinds of integrals are called orthogonal functions, where they give us 0. So if we have a function f of x and we multiply it by another function g of x, and we integrate that product between some interval a and b, and if we find if it gives us 0, then this is what's called an orthogonal function. So as I've stated earlier, we're going to use the results of these integrals to find the Fourier constants, and we're going to start with an. So how we're going to do that is we're going to take cos mx, we're going to multiply it by f of x, okay? So f of x is the function that we're going to find the Fourier series for. It could be any function. So for example, f of x is equal to 2x. And we're going to integrate that across our period minus pi to pi. And of course, our integral is with respect to dx. So what this means is that we can now replace this f of x, this function that we're integrating with, in the form as the Fourier series. So we're going to substitute the Fourier series in place of f of x. So that's the next step. So we have the integral from minus pi to pi, and we remember what the Fourier series is. It's a naught over 2 plus the sum, where we have variable n that starts from 1, goes to infinity, of an cos nx plus bn sine nx. And now we're going to multiply this by cos mx. And all this is being integrated with respect to dx. So let's multiply this out. So when we multiply this out, what we get is the integral from minus pi to pi of a naught over 2 times cos mx. So we write that down. So what we're going to do as well is we're going to multiply it by each term,
and we're also going to split the integral. So we're going to write the integral for each term within the brackets. So we're going to say this is with respect to dx. Then we're going to find the integral from minus pi to pi of the second term. So that would be the sum of n is equal to 1 to infinity of an cos nx cos mx, because we're multiplying it, dx, and then the last term is the integral from minus pi to pi of bn sine nx, don't forget the sum. So we have bn sine nx cos of mx dx. Okay, so what we can also do is we can recognize that we can interchange this integral and this sum. Okay, so what I'm saying is that we can swap the position of this integral and this sum around, because an is a constant and bn is also a constant. So that's what I will do. It's still the same thing though. So I'm writing the summation in front, n is equal to 1 to infinity. Okay, and I've taken out an as a constant, and then I write the integral from minus pi to pi. And then I do the same here. So I write the integral first. So n goes from 1 to infinity. And I take out bn as the constant, and I integrate from minus pi to pi. So let's look at these integrals now. So you can see that we have cos nx, cos mx, sine nx, and cos mx. So these are looking very much like the integrals that we had derived. So let's look at this last integral, sine nx and cos mx. What does this equal to? So if we have cos mx sine nx, this gives us 0 regardless of if m is equal to n. So this last term of the integral is going to be equal to 0. So let's just indicate that. So this entire term is going to equal to 0. Then we have cos nx and cos mx. Okay? So let's see what that is. So we have cos mx, cos nx, and we see that we get a value of pi if m is equal to n, and we get a value of 0 if m is not equal to n. So this integral is only going to take on the value of pi for specific values of n and m if they are the same. And lastly, for the first term, we have cos mx, and the integral of cos mx, as we saw earlier, is just 0 as well. So that first term is 0. So this is equal to 0. So what are we left with? Let's substitute in some values of n. So n starts from 1, and we know that this integral is going to take on the value of 0, right? So we have a1 times 0. Then we have a2 times 0. We have a3 times 0. We can carry on like that. And at some point, since we're considering all values of n, n is going to equal m. So when n becomes m, this integral is going to take on the value of pi. And it will carry on being 0. So if we're considering the first term, the second term, the third term, that is a1, a2, a3, we can create m to take on that value of that term, and we will get pi. So if a is equal to 3, so if a is equal to 3, sorry, if n is equal to 3, and then we're finding a3, then that term wouldn't be 0, it would be pi, and everything else would be 0. So that's how it actually works. So this entire integral becomes pi for that value of m. So that's the result. So what we have said is that this integral fx cos mx is equal to a m times pi. So what we can do is that we can rearrange this. We can find the value of am. Am is equal to 1 over pi times the integral from minus pi to pi of f of x times cos mx dx. So when we expanding out our Fourier series and trying to find the Fourier series, let's just say we wanted to find A3 as we've just indicated now as an example. And we also gave a random example, f of x is equal to 2x. So if we wanted to find the third Fourier coefficient A3, it would simply be 1 over pi integrating from minus pi to pi of f of x, which is 2x as the random example, and we want 3, so cos 3x. And this is a simple integral to evaluate, and we're able to find that Fourier constant like that. So we don't do it for each constant. We find a general expression for n or m, and we are able to substitute in the constants like that. So we will now do the same to find Bn. So what we'll do is we'll take the function f of x, we'll multiply it now by sine mx, and we'll integrate that between minus pi and pi. And as we had done previously, we will proceed in the same manner. We'll substitute in the Fourier series for f of x. So we have the integral from minus pi to pi, substituting in the Fourier series. So that's a naught over 2 plus the infinite sum, where n starts from 1, goes to infinity. An cos nx plus bn sine nx. Being multiplied by sine mx. Dx. So as we had done just now, we will multiply it for each term, and we will separate out this infinite sum and this integral, and we will put it into the form of the integrals that we had shown earlier. So if we do that, we get integral from minus pi to pi. We have a naught over 2 times sine mx dx, then plus we have our sum, then we have our constant an, then the integral from minus pi to pi of cos nx times sine mx. And just as was the case in the previous derivation that we did, this entire integral becomes 0 because sine cos mx nx times sine mx, this gives us 0 for regardless if n is equal to m or not equal to m. And then the last term is the sum, and we have bn, and we have integral sine nx and sine mx.
it's exactly the same. So this first term also gives us 0 because of the sign mx here. So if we write this out, then we find that we only get a value for this integral if n is equal to m. So if we take different values of n, as we had done, we can have b1, we'll have 0, then we have b2 times 0, plus b3 times 0, and it could go on like that until n takes on the value of m. Then we have bm, and we'll have pi. So this integral takes on the value of bm pi. Now, if we solve for bm, then we find that we get 1 over pi integral minus pi to pi of f of x sine mx dx. So we have found those two constants. So the last one we need to do is to find a naught. So we have already derived that an is equal to 1 over pi integral from minus pi to pi of f of x times cos nx dx. So now what we want to determine is a naught, the first term in the Fourier series. We just make n equal to 0. So we have 1 over pi integral from minus pi to pi f of x and cos of 0 essentially. Let's substitute it. So cos of 0 is equal to 1. So what that becomes is 1 over pi, the integral from minus pi to pi of just f of x dx. So these are essentially the three relations we need to determine the Fourier constants. So I think this is best illustrated in an example, and that's what we're going to do now. This is the example that we're looking at. We have a periodic function. So from minus pi to pi over 2, minus pi over 2 that is, the function is taking on the value of 0. And then from minus pi over 2 to pi over 2, the function is taking on the value f of x is equal to 4. So it's a constant y value. And then from pi over 2 to pi, it's again taking on the value 0. So our period is from minus pi to pi, and we're going to find the Fourier series between this region. So if we were to describe this function analytically, what we would say is that f of x is equal to 0 between minus pi and minus pi over 2. F of x is equal to 4 between minus pi over 2 and pi over 2. And f of x is again equal to 0 between pi over 2 and pi. And we state that it's a periodic function by saying that every 2 pi repeating units, this graph will take on the value of f of x as we have defined it. So we are now going to find the Fourier series for this illustration. As we had derived earlier, we can just go back to it. We saw that a naught is equal to 1 over pi times this integral. So that is the first thing that we're going to determine. So let's just write it again. A naught is equal to 1 over pi times the integral of minus pi to pi of f of x dx. So now we're going to integrate between minus pi and pi and put in each value of the function between these integrals. So we have 1 over pi, and then expanding it out, we have firstly the integral from minus pi to pi minus pi over 2. And that value is 0. Then we have the integral from minus pi over 2 to pi over 2. And that value is 4. And then lastly, from pi over 2 to pi. And that is also 0. So the integral of 0 is just 0, so we don't need to waste our time with that. So what we're left with is 1 over pi, and we have the integral of 4, so that is 4x being integrated from minus pi over 2 to pi over 2. So we have 1 over pi into, if we substitute pi over 2, we're going to have 4 divided by 2. So that just gives us 2. So we're going to have 2 pi. And the minus will give us a plus. And again, 4 divided by 2 is 2. 2 pi plus 2 pi is 4 pi. 4 pi divided by pi is just going to give us 4. So A naught is equal to 4. So we have essentially found the first term of the Fourier series. So now we can proceed with the rest of it. We can refer back to the derivation, and we can see that the an term is equal to 1 over pi, integral from minus pi to pi of f of x times cos nx dx. And we can do our substitutions as we had just done it. So we have 1 over pi, and the integral from minus pi to minus pi over 2 was 0. So we have 0 cos nx. Then we had integral from minus pi over 2 to pi over 2, and that was 4. F of x took on the value of 4. We had 4 cos nx. And lastly, we had pi over 2 to pi, and that was 0 again. Let's just remind ourselves once more. 0, 4, and 0. And this is the derivation that we had used, that we had developed. So this first term is going to give us 0. So this term is also going to give us 0. And we're left with the second term. So we have 1 over pi. And we can integrate it. The integral of cos is sine. So let's just take out the 4 as well. Take the 4 out. So we have 4 over pi. And we can integrate cos nx. So the integral of cos is sine. So we have sine nx over n. And we are integrating that between minus pi over 2 and pi over 2. Okay, so we can proceed with that substitution. So we have sine of n times pi over 2. Let's say n pi over 2 over n. And then minus sine of minus n pi over 2 over n. So here we need to just remember a trig identity. So the trig identity is that if we have sine of, let's just say minus 90 degrees, or sine of minus pi over 2 radians. This is actually equal to minus sine 90 degrees, or just minus sine pi over 2. So essentially this term is minus sine and pi over 2. So if we bring out the minus, we can have a minus here and a minus here, and it's going to give us a plus. So what we'll do is we'll write plus here, and we'll remove this minus here. So these two terms are essentially the same, and we're adding them. So 1 plus 1 is 2, so 4 times 2 is 8. So what we're left with is 8 sine n pi over 2 divided by pi n. So now we just need to understand how we can get these coefficients out of this result. So this is a general result for an. So this is what an is equal to. What we would do is we would now consider different values of n. We can consider even numbers and odd numbers. Let's just say we consider even numbers. So that would be n is equal to 2, 4, 6, etc. So let's just remind ourselves what the sine graph looks like. Okay, so we start off at 0, reach 1, we go down to minus 1, then it repeats itself like that. So that is 0, that is pi over 2, that's pi, so that's 3 pi over 2, and this is 2 pi, that's 2 pi, and this is 5 pi over 2, and this is 3 pi. This is 3 pi here, and this would be 7 over 2 pi. Sorry, 7 pi over 2. So we can carry on writing like that. So if we have even numbers of n, what is going to happen? So let's just say n is equal to 2, right? So we substitute 2 here. So we're going to have 2 pi over 2, the 2's will cancel off, and we'll essentially have sine of pi. And sine of pi is 0, okay? So this entire term becomes 0. So an will become 0 here. If we substitute 4, we'll have 4 pi over 2, so 4 divided by 2 is 2, so we have sine of 2 pi. So sine of 2 pi is also 0, so you can see that there's a trend, and all of these things will be equal to 0. So for even numbers, we can generalize this and say that an is equal to 0, okay? So now what we're going to do is consider this for odd numbers. So n will take on the value 1, 3, 5, 7, 9, 11, and so on. So let's just say n takes on the value 1. So we have sine of just pi over 2, and sine of pi over 2 is 1. So when n is equal to 1, this value an takes on the value 8 over pi n. And let's just say we substitute 3. So we have sine 3 pi over 2. Sine of 3 pi over 2 is minus 1. So we're going to have minus 8 over pi n. And if we substitute 5, we have sine of 5 pi over 2. Sine of 5 pi over 2 is 1. So we're going to have 8 over pi n. And then if we substitute n is equal to 7, so we have 7 pi over 2, we can see that it's minus again. So we have minus 8 pi over n. So this will continue like that. So what we see is that for every alternate odd number, we have positive coefficient. We have 8 pi over n. And for the remaining ones, we have minus 8 pi over n. So what we can see here is that, so we'll say for n is equal to 1, 5, 9, etc., then an is equal to 8 over pi n. Then for n equal to 3, 7, 11, etc., an is equal to minus 8 over pi n. So we are now almost done. We are literally almost complete with writing our Fourier series. There's just one other term that we need to determine, and that is bn. And we had derived this earlier as well. We can just show you where. So we had done it here on the top. We had seen that bm was this expression here. So that's what we're going to use to find that term. So bn was equal to 1 over pi times the integral from minus pi to pi. Then we had f of x and sine nx. So we substitute this in. For the function that we have considered, we're taking the integral from firstly minus pi to minus pi over 2. Let's just remind ourselves once more because it was a little while back. Minus pi to minus pi over 2, 0, then 4, and then 0 again. So we had 0 sine nx, then plus from minus pi over 2 to pi over 2, we had 4 sine nx, and lastly from pi over 2 to pi, we add 0. Okay, first and third term will disappear as they are 0, and we have 4 sine x. We can bring out the 4 in the front, so we have 4 over pi. And we integrate. Integral of sine is minus cos. So we have minus cos nx over n, and we're integrating from minus pi over 2 to pi over 2. Okay, we don't need to proceed any further because we know that cos of pi over 2 is equal to 0, and so is cos minus pi over 2. And for all multiples of that, it will give you 0. So this is equal to 0. So what we're saying is that there are no bn terms. Bn is just equal to 0. So we can write our Fourier series. There will be no sine terms in our Fourier series. There will only be cos terms. So there are ways in which we can decide whether we can need to actually evaluate some of these integrals. And it depends on whether it's an even and odd function and some combination of it. And there is some upcoming videos in this series that will actually identify and assist you to be able to see how you can simplify the calculations just by identifying if it's an even or odd function and some combination of that. So anyway, writing out our Fourier series, we have f of x is equal to a naught over 2 plus our infinite sum starting from 1 to infinity of an cos nx plus bn sine nx. So we know that this bn is equal to 0. We had just shown that. We're only going to have these cos terms. And a0, if you'll remember, was equal to 4. And an, we had seen that it actually depends on odd numbers only. And every alternate odd number was negative. So let's just go back to that. So here was a0. And we had seen that is equal to 4. And an, we had seen that there are no even numbers. There are no even number coefficients. And for the odd numbers, we had 8 pi over n and minus 8 pi over n. So we will just substitute all of those things. So we have 4 over 2, that just gives us 2. And we can say plus that 8 over pi, we can bring it out as a common factor. So this is the 8 pi we're talking about. We'll just bring that out as a common factor. So we have 1 over n. So let's just refer to it on the top here. So when n is equal to 1, we have a positive number of this coefficient. So we have 1 over n there, so that's 1 over 1. So we have just cos x. Remember, it's cos nx, n is equal to 1. And remember, even numbers was just equal to 0, which we had shown. So now we go to 3. And 3, we see we have a negative number. So we have to write minus 1 over 3, because it's 1 over n, cos 3x. And then we now need to substitute in 5. And 5 we see is a positive. So we have 1 over 5 cos 5x. So I think you can see where this is going. We can continue in that manner. So we just change it from plus, minus. So we have minus 1 over 7 cos 7x. And we can continue like that. So this is essentially it. This is the Fourier series. We have written the Fourier series for our first function.
Hi there. In this video, we're going to talk about Dirichlet conditions. So what these conditions are is basically something that describes if a Fourier series can be written. We said in the introduction to this video series that one of the advantages of writing a Fourier series as opposed to a Taylor series or Maclaurin series is that the Fourier series can be written for functions that are discontinuous. So the question is, how broad or how wide can we actually write the Fourier series for different kinds of functions? And the answer to that question is the Dirichlet conditions. It basically says, okay, for these functions you can write the Fourier series and for these functions you can't. So there are two conditions. The first one is that the Fourier series can be written for functions that are defined and that are single valued. So we can assess if a function is single valued if we draw a line through it and it just cuts the graph once. An example of this could be some kind of function like that, and we draw a line through it and we see that it cuts the graph once, so therefore it's single valued. So an illustration of a function that is not single valued would perhaps be a circle. We see that if we draw a vertical line through it, we see that it cuts the graph twice. So this is not a single valued function. So if we have something like y is equal to plus minus the square root of 4 minus x squared, the equation for this circle, then we can't actually write the Fourier series for a function that has this in it, because it is not single valued. The single or the other condition, number 2, says that f of x has to have finite discontinuities. So I mentioned just now that we can write the Fourier series for a function that has discontinuities, and this is one of the advantages of using the Fourier series. So an illustration of that could be something like, we have a certain function up until a certain point, and beyond that point we have another function, okay? So we can actually write the Fourier series for this kind of situation, even though the function is discontinuous. We modify it slightly, and we'll look at that in upcoming videos, but the moral of the story is that it can actually be done. So this is an example of a function that is piecewise continuous. So that's piecewise continuous. So what would be an example of functions that are not piecewise continuous? So for which kinds of functions that have discontinuities could we not write the Fourier series for? Well, we would not be able to write the Fourier series for functions if they have infinite discontinuities. So if a function has infinite discontinuities, we cannot write the Fourier series. So some examples with infinite discontinuities with which we cannot write the Fourier series for would be things like f of x is equal to tan x. If we remember our trigonometric graphs, we would remember that tan x has an infinite discontinuity at x is equal to pi over 2. Another example would be f of x is equal to maybe 2 over x. So there we can see that there's an infinite discontinuity at x is equal to 0. So these would be examples of infinite discontinuities with which we would not be able to write the Fourier series, or the Fourier series would not converge for these kinds of examples. So just to summarize once more, f of x must be defined, single valued, and must have finite discontinuities, if that's what we're considering. That is, it must be piecewise continuous. In this video, we're going to consider an additional example of how to write the Fourier series for different kinds of functions. So this is the function that we're considering. So we're saying that f of x takes on the value of minus x, that's y is equal to minus x, between minus pi and 0. And thereafter, it just takes on the value of 0 between x is equal to 0 and pi. And we will complete this by saying that it's a periodic function by taking on the value of f of x every 2 pi units. 2 pi is our period. So how do we go about writing the Fourier series for this? Well, we have to determine our Fourier constants. And the first one that we do is a naught. A naught is equal to 1 over pi multiplied by the integral from minus pi to pi of simply f of x dx. So this is equal to 1 over pi, and then we simply substitute f of x, so that's minus x, between minus pi and 0, and of course 0 after that, so there will not be any term. So let's substitute that in. So from minus pi to 0, we have minus x dx, and then we have from 0 to pi, 0. So the integral of minus x is just minus x squared over 2. That's integrated from minus pi to 0. So if we substitute in 0, we get 0, and then minus and a minus would give us a positive. So we're left with pi squared over 2. So 1 over pi multiplied by pi squared over 2. So this gives us just pi over 2. So that's what A naught is equal to. So next we determine AN and BN. So AN, if we remember, is the integral from minus pi to pi. There's also a 1 over pi in front. And it was f of x times cos of nx. So we do our substitutions. So we get 1 over pi. And we have the integral from minus pi to 0. And that was minus x. So we have minus x cos nx dx, and then plus 0, the integral of 0. So this integral is obviously going to give us 0. So we need to evaluate x cos nx. So we have two functions that are being multiplied. So we have to use integration by parts. So let's just remember what that is. So how we would do it is we would say it's the product of two functions u and dv. And that's equal to uv minus the integral of v du. So we essentially choose one function to differentiate and one function to integrate. So the function that we're going to differentiate is x. So that's what u is. So we'll say that u is equal to x. That means that du is equal to dx. And what we're going to differentiate is dv. So we'll say that dv is equal to cos nx dx. So dv is equal to cos nx dx. And if we integrate this, then we see that v is simply equal to sine nx divided by n. So what we now need to do is substitute these things in. So we have uv, therefore we'll have x times sine nx over n. So as I've just stated now, the first term is uv, so that will be x sine nx divided by n. And also recall that this is a definite integral that we're considering, so it's uv, but we have to integrate this as well. So what we're going to do is also swap the order of integration. So the minus pi and the 0, we're just going to swap that around just to make it a bit easier. So we're going to have 0 to minus pi. And since we have done that, we have removed this negative. So the next term is a minus. And now we have the integral. So we're going to do the same thing. We're going to reverse this order of integration. So we're going to have from 0 to minus pi. And then it's v du. So v is sine nx over n, and then du is just dx. So we're going to have sine nx over n dx. So now we can evaluate this. So sine of minus pi is just 0, so that's not going to do anything. And then sine of 0 is also 0 as well. So now here, so what's going to happen is that we are going to integrate sine nx. Okay, so the integral of sine is minus cos, so that's what we're going to put in. And remember that cos of minus x is just the same thing as cos of x, so we need this. So long story short is that it's going to become plus. So we're going to have cos nx divided by n squared from 0 to minus pi. So when we put in cos of minus pi, this is where we're now going to use our trig identity. So let's just write that again. So cos of minus x is equal to cos of x. So when we put in minus pi, all that we're going to do is we're just going to get cos of pi. So we have 1 over pi into cos nx, sorry, cos n pi divided by n squared, and then minus 1 over n squared, because the cos of 0 is 1. So we'll just have 1 over n squared. So if we were to simplify this, when we pull out n squared as a common factor, what we get is 1 over pi n squared into cos of n pi minus 1. So this is what an is equal to. So now we just have to understand how we will actually substitute this in the Fourier series. So the easiest way to do this is to just do it for even numbers and for odd numbers and all of these things. So let's just remember what cos looks like. That is the graph. So we have 1 and we have minus 1. And it starts off at 1 when x is equal to 0. So then it goes down to 0 when x is equal to pi over 2. And then it goes down to minus 1 at when x is equal to pi. And then it repeats itself like that. Okay, so that's pi over 2. That's pi. So this is 3 pi over 2. And that is 2 pi. And that is 5 pi over 2. And that is 3 pi. And so on. So let's have a look at even numbers. So even numbers would be n is equal to 2, 4, 6, etc. So if n is equal to 2, so we substitute 2. So it means cos of 2 pi. Cos of 2 pi is equal to 1. So 1 minus 1 is 0. Okay, so this entire term is 0. So it's the same thing now if we substitute 4. So if we have cos of 4 pi, we're going to get 1 again. So that's 4 pi here. There's 4 pi. So 1 minus 1 is 0. So we see that we get 0 for even numbers. So an is equal to 0 for even numbers. So now we try odd numbers.
let's say n is equal to 1, 3, 5, 7, etc. So if n is equal to 1, so we have cos of pi. So cos of pi is minus 1. So minus 1 is minus 2. So what we have here is minus 2 over pi n squared. So let's now check 3. So if we have 3, that's cos of 3 pi. Cos of 3 pi, so there's 3 pi here. Cos of 3 pi is minus 1. So again, that gives us minus 2. Minus 1 is minus 2. And we have the same thing, minus 2 over pi n squared. So we can see that 1, 3, 5, etc. So for odd numbers, we have minus 2 over pi n squared. So for even numbers, it's equal to 0. And then for odd numbers, an is equal to minus 2 over pi n squared. So that is an. So we now repeat the same process for bn. We would remember that bn is equal to integral from minus pi to pi f of x, but this time multiplied by sine nx. So all we do is just substitute that in. So we have 1 over pi. We integral from minus pi to 0 of minus x sine nx dx. And the remainder is from 0 to pi, and that value was 0. So that's not going to give us anything. So this is all we're integrating. And we use integration by parts in the same manner. So let's just write down that formula again. So we have u dv equal to uv minus the integral of v du. So we'll differentiate x and integrate sine nx. So that means that we'll set u to equal to x. That means that du is equal to dx. Then we'll set dv to be sine nx dx. And if we integrate that, we get that v is equal to minus cos nx divided by n. We can now substitute all of these things inside our equation and determine bn. So we have 1 over pi and then uv, so u is equal to x and v is equal to minus cos nx. So it's minus x cos nx divided by n. And this is integrated from 0 to minus pi. So we have swapped around the order of integration as we had done with an. And then we're going to say plus. So there's a minus here and a minus here, so that will give us a plus. And we have the integral from 0 to minus pi, so we've just swapped that around again. And we have cos nx divided by n dx. So we can now evaluate this. So if we do that, we'll get 1 over pi again. We'll just keep this the same, so we'll just write it as it is once more. So we have minus x cos nx divided by n, integrated from 0 to minus pi. Then we have plus. Then the integral of cos is sine. So we're going to have sine nx divided by n squared from 0 to minus pi. So the integral of sine of minus pi or pi is just going to be 0. So this first term is going to give us 0. And sine of 0 is also 0. So there isn't going to be any term here. So now we can only evaluate this first term. So we have 1 over pi, and now we do our substitutions. We can substitute in A minus and a minus is going to give us a plus. So we're going to have pi times cos n pi divided by n. And then we're going to have 0. So if we just substitute in 0 here, we're just going to get 0 because in place of x. So there isn't going to be any term there. So that pi and that pi is going to cancel out. So what we're left with is just cos nx over n. And now if we substitute in our different values of n, so if n is odd or n is even, so let's just say now that n is odd. So if n is odd, we're going to have cos of, sorry, this is a pi. We're going to have cos of pi, then cos of 3 pi, cos of 5 pi. And then if we look at our graph, so if we have odd numbers, there's 1, 3, etc., we're going to have minus 1. So for odd numbers, we're going to have minus 1. So if n is odd, then it means that bn is equal to minus 1 over n. So now if n is even, then it means that bn is now equal to 1 over n because we're going to have positive numbers. So that's easy to see as well. So there's it here. So 2 pi, 4 pi, etc., we see that it's equal to 1. So now we can substitute all of these things in our Fourier series. That means that f of x is equal to, so remember the general form of the Fourier series, it's a naught over 2 plus the sum, where n is equal to 1 to infinity, and we have an cos nx plus bn sine nx. So a naught was equal to pi over 2, I believe. We can just go up and see that. There was a naught, and it was pi over 2. And an was minus 2 over pi n squared, and that was for odd numbers only, and for even numbers we saw that it was equal to 0. And lastly, bn was minus 1 over n or 1 over n. So substituting all of these things, we have pi over 2 divided by 2, that gives us pi over 4. Then we have minus, so remember that it was minus 2 over pi n squared, so bring out the 2 over pi as a common factor, and then the remainder of the terms of n was 1 over n squared. So we have cos of x, so let's just remind ourselves, an was equal to minus 2 over pi n squared. This was for odd numbers, okay? So the 2 over pi, we took it out as a common factor in front. Now we have 1 over n squared. So cos of 1, if n is equal to 1, is just there. Then we have 3. Remember, we don't have any even numbers, so we'll ignore that. So we'll have 1 over 9. Then cos 3x. Then we have 5. So we have 1 over 25. Cos 5x. And so on. Then we have the sine terms. So n was 1 over n, minus 1 over n for odd numbers and 1 over n for even numbers. So we'll just say it's minus, so we'll just put the minus in front. And then what we'll do is that for every odd number within the bracket, we'll say it's a positive number. And then for every even number, it's a negative number. So we'll have sine x So a minus and a minus will give us, sorry, a minus and a plus will give us a minus. So therefore, for odd numbers, we have negative, so that corresponds. So now for the first even number, we'll say minus, so a minus and a minus gives us a plus. That will correspond to the positive for the even number. So we have 1 over 2 times sine of 2x, and it carries on like that, 1 over 3. So every alternative coefficient, it will alternate between positive and negative. So we have plus 1 over 3 sine 3x, and so on. So this was the Fourier series for another example. And the only thing that we had to do differently from the previous example that we had done was that we had to use integration by parts to evaluate the integral involving x. So for this portion of the graph, we had x cos x and x sine x. And we had to use integration by parts to evaluate the Fourier series for these portions. But that was not very difficult, and we can see how we can calculate the coefficients anyway. So thank you very much for watching. In the upcoming videos, we will consider generalizing the Fourier series for any kind of period. Remember that these periods now are valid for 2 pi. So how would we write the Fourier series for any kind of period? So generalizing it, and how we would write the Fourier series for half-range series, and a few other considerations. In this video, we're going to talk about what happens when we write the Fourier series at a point of discontinuity. So we kind of have been doing this so far in the videos where we've been writing the Fourier series for a few types of functions. So let's just look at what happens when we have a point of discontinuity. So we could have one function at a certain point, whatever it may be, and we have our point of discontinuity. And then we have another function. So the function is piecewise continuous, and we said that this is one of the conditions for which we should be able to write the Fourier series for. So one of the advantages is that we can represent a function like this using a Fourier series. But the question is, what do we get when we try to see the Fourier series at this point of discontinuity? So at x1, we have two y values. We have the y value associated with this top function. Maybe we can call that y1. And we have the y value of this other function, y2. So we remember that the Fourier series consists of infinite terms. So f of x is equal to a naught over 2 plus this infinite sum where n starts from 1 and goes to infinity of an cos nx plus bn sin nx. So the more we increase this number of terms that we write the Fourier series for, the better it will approximate this function. So the more terms we have, the more this sum will start to look relatively like this function. But what happens at this point of discontinuity? What value does the Fourier series take at x1? Does it take the value y1 or y2? Well, the answer is that it takes a value in between. So it literally takes on the average value. The Fourier series converges to the average value. So at x1, or maybe we'll just write f of x1. So what it approaches is the average value. So it's y1 plus y2 divided by 2. So if we write the Fourier series for this function like this, for this period, and we substitute in x1 into this Fourier series for all our cos terms and sine terms and whatnot, and then we try to get a converged value, we try to assess what the Fourier series converges to at x1, we will find that it's the average. So y1 plus y2 divided by 2. So it's this value in between. So we can just illustrate that point with just a simple example for a function that we have written for. So we have, there's our point of discontinuity at x is equal to 0, and from minus pi to 0 we have the value 0, and then from 0 to pi, then we have the y value taking on a. So if we were to write the Fourier series at x is equal to 0, this is our point of discontinuity, we should find that the Fourier series at this point will take on the value a over 2. So let's try to see that quickly. Let's just write the Fourier series. The Fourier series, we remember, we wrote it on the top. So f of x is equal to a naught over 2 plus sum an cos nx plus bn sin nx. So we'll just determine this coefficients quickly. So if we look back to the previous videos and remember what those coefficients are, so we'll remember that a naught is equal to 1 over pi times the integral from minus pi to pi of f of x dx. And we substitute these things in. Well, from minus pi to 0, we're going to have 0, so there's no point in substituting that in. However, from 0 to pi, we have the value a, so we'll just do that. So we have 1 over pi, integral from 0 to pi of a dx. And if we evaluate that, we'll get 1 over pi. And the integral of a is just ax, since we're integrating with respect to x. And that's being done from 0 to pi. And if we substitute in pi here, we'll see that this pi will cancel out with this pi that's in front. So what we'll be left with is a. So a naught is simply equal to this value a. So let's do it for the rest of the coefficients. An is equal to 1 over pi, integral from minus pi to pi of f of x cos nx. So f of x is equal to a from 0 to pi, and we substitute that in. So we have 1 over pi, 0 to pi, a cos nx dx. And if we integrate this, we get 1 over pi, and we'll have a integral of cos is sine. So we have a sine nx divided by n, integrated from 0 to pi. So sine of pi and all multiples of pi will give us 0, so there is no value there. And also sine of 0 and of course multiples of 0 will be 0. So this entire term is just equal to 0. Sorry, 0, not a. That means that an is equal to 0. So there's essentially no cos terms in our series for this function. So just quickly, bn. So bn is equal to 1 over pi, integral from minus pi to pi of f of x sine nx dx. And we're integrating from 0 to pi once more, and our function is just the value a. And we have sine nx, and we just integrate this. So that's 1 over pi. The integral of sine is minus cos. So we have minus a cos nx divided by n from 0 to pi. So we can substitute in pi and 0. So we have 1 over pi. And we have minus a cos pi x, sorry, n pi over n. And we substitute 0. So cos of 0 is just 1. And of course, we have minus. So minus and a minus gives us a plus. So we have plus a over n. A over n, because cos is 1. So we can just bring out a over n. Sorry, there's an a here in front as well. So we can bring out a over n as a common factor. So we have a over n pi. And this a over n, well, that's just 1 because we brought it as a common factor. And now we have cos n pi. So as we had done previously, we look at even numbers and odd numbers. So for even numbers, cos of n pi takes on the value of 1. So you can look back at our previous videos where we looked at examples, and you can see how we had drawn out the cost curve and looked at all of these values of pi and multiples of pi, and we show for even numbers and odd numbers what cost becomes. So cos of n pi is equal to 1 for even numbers, and if we put in 1 here, then we see that 1 minus 1 gives us 0. So Bn is equal to 0 for even numbers. So Bn is equal to 0 for even numbers. So our Fourier series will just have odd numbers. So for odd numbers, cos of n pi is equal to minus 1. And if we put in minus 1 into our term here, we get 1. Well, minus and minus gives us plus. So we have 1 plus 1 is 2. So we have 2a over n pi. So for odd numbers, Bn is equal to 2a over n pi. So we can write our Fourier series out quickly. And then we have f of x is equal to a naught over 2. So we had seen just now that a naught was equal to a, the value a in the function. An was equal to 0. And Bn, we only had Bn for odd numbers, and they took on this value 2a over n pi. So we have a naught over 2. So a naught was 8. So we have a over 2. And we have plus. Remember that there's no an terms. So there's no cost terms inside our series. And in our coefficients, we have 2a over n pi. So 2a over pi is a constant. So we can bring that in front of the sum. So we have 2a over pi. Then we have odd numbers. So the first term will be bn sine nx. So bn will take on the value 1. So we have 1 sine nx, and n is 1. So we have sine x. Then the next odd number is 3. So we have 1 over 3, because it's 1 over n, sine 3x plus 1 over 5 sine 5x, and so on. Okay, so what we wanted to do was to see what value it takes at the point of discontinuity. So what does the Fourier series converge to at x is equal to 0? So how would we do this? Well, we have our Fourier series. All we do is we just substitute x is equal to 0 and see if we get a over 2. Okay, so our Fourier series is made up of sine terms primarily. So sine of 0 is 0. So that is 0, that is 0, that is 0. So all our sine terms become 0. And of course, there's no coefficient here because it's being multiplied by 0. So that means that it's equal to a over 2. So our Fourier series converges to a over 2 at the point of discontinuity. So it is the case that when we try to evaluate the Fourier series at this point of discontinuity, we see that it takes on the average value of the two functions. Yeah. In this video, we're going to talk about even and odd functions in the context of Fourier series. So basically, it really helps to identify if the function that we're writing the Fourier series for is an even and odd function. Simply by just doing that, we can simplify a lot of our work. And just by judging that, we'll be able to say, okay, a Fourier series will contain only sine terms or only cosine terms or whatever it is the case. So let's just do a quick revision of what even and odd functions are. We can start off with even functions. So an even function is a function where if we substitute minus x into the function, we get f of x. So the simplest illustration of this is just to consider y is equal to x squared. So just a parabola. So we have a parabola, y is equal to x squared. So we can see that if we substitute minus x inside this, then we'll still get the same value. For example, if we say f of 2, or rather f of minus 2, then we're going to get minus 2 squared, which is 4. So we can see that regardless of whether it's x or minus x, we'll still get the same y value. So the moral of this story is that an even function is symmetrical about the y-axis. So if we put a mirror on the y-axis, whatever we will see on one side, we will see on the other side. So symmetrical about the y-axis. So since we're talking about Fourier series, we have to consider the trigonometric terms. So we can look at cos x. So if we just quickly draw the graph of cos x, so we have minus pi, pi over 2 and pi over 2 and pi. So we know that it starts off at 1 at minus pi, it goes to minus 0 at pi over 2, then it goes up to 0, and it carries on like that. Okay, this is drawn quite poorly, but I think you get the idea. So that's minus pi, that's pi over 2, or minus pi over 2. So that's 0, so that is pi over 2, and that's pi. So we can see that we get minus 1 at minus pi there, and we also get minus 1 at pi. Okay, so in other words, cos of minus x is equal to cos x. So this is a general trigonometric identity which many people will be aware of. So this means that it's an even function. It is symmetrical about the y-axis. So these are even functions. So let's look at odd functions. So for an odd function, what happens is f of minus x is equal to f of x. So the easiest illustration of that would be perhaps the graph y is equal to x cubed. So x cubed looks something like this. Okay. So this is f of x is equal to x cubed. So if we were to substitute minus 2 here, then we get minus 2 cubed, and we see that we get minus 8. So similarly, if you put in f of 2, then you'll see that you would get 8. So what this is saying is that f of minus x is equal to f of x. So what happens here is that for odd functions, we see that they are symmetrical about the point of origin. So we kind of draw this diagonal line like this, okay? And we put this mirror along this diagonal line. So this portion is symmetrical about that portion. So odd functions are symmetrical about the point of origin. So they are symmetrical about the origin. So in terms of the trigonometric graphs, so we can have sine x. We'll just draw sine x quickly. Okay, so the sine graph looks something like that. Carries on and goes on like that, okay? So here we have minus pi over 2, because that's minus 1. And here we have pi over 2, sorry, that's 1, and that is pi over 2. So sine of 90 degrees or pi over 2 radians is 1, and sine of minus pi over 2 is minus 1. And you can see that we can draw our dotted line diagonal. And if we put our mirror on the diagonal, we can see that we have something there and it's symmetrical about there. So those two kind of peaks are symmetrical about the origin. That's why it's an odd function. So numerically we can write it that sine of minus pi over 2 is minus 1, whereas sine of pi over 2 is 1. So this indicates that it's an odd function because f of minus x is equal to minus f of x. So sorry, there should be a minus here. So we can have functions that are neither odd nor even. So an example of this could be something like we have some oscillation like this. We can see that this is neither, it's not symmetrical about the y-axis, neither is it symmetrical about the point of origin. Okay, so what we see here, we don't see on this side here. Neither is it symmetrical about, so this is neither odd nor even. Another example of a graph that is neither odd nor even would be something like maybe a straight line, something like that. Y is equal to 2x plus 3. So we can see that it's not symmetrical about the y-axis, nor is it symmetrical about the point of origin. So we also now want to look at what happens when we take the product of odd and even functions. So this is very important now to understand the implications to the Fourier series. So if we have an even function, and if we multiply it by an even function, then what we get is an even function. So for example, we can have f of x equal to something like x squared, and then we can have g of x equal to cos x. So if we take f of x and we multiply it by g of x, then we get x squared cos x, and this is an even function. So the analogous to this is if we have a positive number and we multiply it by a positive number, then we get a positive number. So similarly, if we had an odd function and we multiply it by another odd function, then we get an even function. Analogous to this is if we have a negative number and multiply it by a negative number, then we have a positive number. And lastly, if we had an odd function and multiply it by an even function, then we get an odd function. So analogously, negative number multiplied by a positive number will give a negative number. This affects our work with the Fourier series, and we can illustrate that with some examples. But before that, let's just analyze what even and odd functions do when we try to integrate them. We can take a function. So this would be an even function. And we're integrating from minus pi to pi. And we're saying that f of x is an even function. It's even because it is symmetrical about the y-axis. So if we were to integrate between minus pi and pi, f of x dx, then what we see here is that we have a certain area, okay, from 0 to pi, and it's exactly the same as the area from minus pi to 0. So all that we can do is we can integrate from 0 to pi f of x dx, and then just double it. It's just twice the area from 0 to pi. So that's an important implication of even functions. Conversely, if we look at odd functions, and if we look at something like that being an odd function, it's an odd function because it's symmetrical about the point of origin. And now we integrating from minus pi to pi. And this year we're saying that f of x is an odd function. So in this instance here, if we integrate from minus pi to pi, f of x dx, well, we're going to have a positive area here, okay? And that is going to be counteracted by a negative area here. So the area here will be a positive number, here it'll be a negative number. The positive and the negative will just cancel each other out and they'll be exactly the same. So this area will be 0. So if we had an odd function and we integrate the odd function between minus pi and 0, we're going to get 0. So what does all of this mean in terms of the Fourier series? What it means, firstly, if we consider f of x being an even function. So f of x is an even function. So we will remember that a naught is equal to the integral, okay, 1 over pi times the integral from minus pi to pi f of x dx. And since it's an even function that we're considering, we know that we can just integrate from 0 to pi and just double it as we had shown in the graph just now. So this is the integral from 0 to pi. We multiply it by 2 and f of x dx. Then we can look at an. So an, same story, we have 1 over pi. We have integral from minus pi to pi of f of x cos nx. So what we have here, since we said that f of x is an even function, we have an even function and we are multiplying it by cos nx. And you'll remember earlier, we said that cos is an even function, okay? So we have an even function and we're multiplying it by an even function. So we're going to get an even function. So this entire product is an even function, okay? And since it's an even function, we can just double it as we had done with a naught. So we had 2 over pi times the integral from 0 to pi f of x cos nx. So that's a naught, that's an, and then lastly, bn. So bn, we'll remember, is 1 over pi, integral from minus pi to pi of f of x sine nx. So here we have an even function, that's what we said. We said f of x, we're saying it's an even function that we're considering. And we're now multiplying it by sine. Sine, we'll remember, is an odd function, which we had shown earlier. So just to refresh your memory, we can go all the way back up. You'll see that we said there's cos. We said cos was an even function. And there here we had said that sine was an odd function, okay? And here we had spoke about the multiplication of the various types of function. And here we said an odd function times an even function will give us an odd function. So now we have an even function multiplied by an odd function. So that's going to give us an odd function. So this entire integral is an odd function. But what happens when we integrate an odd function? So when we integrate an odd function from minus pi to pi, we see that it gives us 0. Okay? So this odd function integrated between minus pi and pi is going to give us 0. So what does this mean? This means that if we identify f of x as an even function, we don't even need to bother to determine Bn. Simply by just being an even function, all of the terms associated with Bn is going to be 0. Therefore, we have an important fact that we must remember. And that important fact is that if f of x is an even function, then what it means is that the Fourier series will have only cos terms. So that means we only have to determine an. And we can do it with this simplified expression that we have shown here. So that's the first important fact. And this is considering that f of x is an even function. So we just want to do the opposite as well. We want to consider f of x being an odd function. So we have f of x being an odd function. So if f of x is an odd function, then what we're going to have is an, as before, equal to 1 over pi, integral from minus pi to pi, f of x cos nx. So here we are saying that f of x is odd, and cos nx we know is an even function. So the product of this odd and even function means that it is going to be an odd function. This entire thing is an odd function. So if we're integrating this odd function between minus pi and pi, it is going to be 0, as we had shown just now. So that means that if we identify f of x as an odd function, it means that we don't even need to bother determining an, because it's just going to be 0. We only need to determine bn. And bn is 1 over pi, integral from minus pi to pi of f of x sine nx So we know that we can just integrate from 0 to pi, since this is an odd function, which is what we are defining it. And sine is also an odd function. So this entire thing is an even function. So that means that we're just going to have 2 over pi times the integral from 0 to pi of f of x sine nx dx. So the first fact that we had seen was that if f of x is even, then the Fourier series will have only cos terms. So the second fact that we want to write here is that if f of x is odd, then it means that the Fourier series will have only sine terms. So let's just refresh what the Fourier series is. So we have a naught over 2 plus infinite sum that starts from 1, goes the way to infinity, an cos nx plus bn sine nx. So if f of x is even, then we won't have this bn terms, we'll only have cos terms. That's what we had said, we had written down. So if f of x is even, we'll only have cos terms because bn will equal to 0. So that's what we are saying here. So if f of x is even, then bn will equal to 0, and we'll only have this cos terms. So similarly, if f of x is odd, then an is going to be 0, and we will only have bn, and the series will only contain sine terms.
So those are two important facts. So they simplify our work quite considerably. We don't need to write integrals for two coefficients if we can identify if the function is odd or even. So the third fact that we should just take note of, if f of x is neither odd nor even, then the Fourier series will contain both sine and cosine terms. So these three facts are the most important thing to remember about even and odd functions. So if we see that f of x is neither odd nor even, then we have to find both an and bn because they will be cos and sine terms. So we can just remember one of the examples we had done in the previous videos. Can go back and actually have a look at it. It was along the lines of so we had a function between minus pi and pi over 2. It took on the value 0, and then it went up to a value of 4, and it carried on like that. So this was minus pi over 2, and that was pi, and this was pi over 2, and that was pi. So if we write the Fourier series for this, and that was 4. So if we were to write the Fourier series for this, then we would remember that from the previous video, I think this was the first Fourier series that we had written. So you can look back at the video where we determined the Fourier coefficients and did the first example. So this was that first example. So we had shown in that video that f of x is equal to 2 plus 8 over pi cos x minus 1 over 3 cos 3x plus 1 over 5 cos 5x and so on. So if we look at this function, we can just ask ourselves, is this an odd or even function? Well, we know that even functions are symmetrical about the y-axis. Okay, if we put a mirror on the y-axis, what we'll see on the left-hand side, we'll see on the right-hand side. And what did we say now in terms of our facts that we had written? So the first fact that we had seen was that for even functions, if f of x is even, we will have only cos terms. So we only need to evaluate the coefficient an. And if we look back at the first Fourier series that we had written, then you can see that we only have cos terms. And since this is an even function, we only have coefficients for an. So that first example, if we had known this when we had did that example, it would have simplified our work a great deal because we would have known that we only need to determine an. We would not need to have evaluate bn, evaluate another integral, and all of those things. So this is the advantage of knowing this. So just to summarize once more, we have to identify even and odd functions. We said that even functions are symmetrical about the y-axis. Odd functions are symmetrical about the point of origin. We looked at products of even and odd functions. Product of even and even was even, and so on like that. And then we had looked at integrals of even and odd functions. And then lastly, we put that into context in the Fourier series and saw that if we identify if a function is even and odd or neither, then we can actually simplify our work by only determining one of the Fourier coefficients. Okay. So in this video, we're going to be talking about half-range series. So thus far in the videos, we've been talking about periodic functions which have the period of 2 pi. So we've been looking at functions between minus pi and pi, and we've been considering periodic functions of this nature. So what a half-range series is what happens now if we only have a function that is from 0 to pi. So that's where the half comes in. So let's just say that there is nothing defined from minus pi to 0. So we just have something between 0 and pi. So let's just say we have a function y is equal to 2x between 0 and pi. Okay, so we have f of x is equal to 2x, and this is between 0 and pi. Okay, all our work on the Fourier series thus far has been defined for specifically a period of 2 pi. So if we have a function now between 0 and pi, what do? We want to represent the Fourier series for this kind of function. We want to get a representation of the function between 0 and pi. So what do we do here? Well, the answer is that we make something up, right? So if we are only going to consider the function between 0 and pi, we could literally put anything between minus pi and 0, and we could write the Fourier series as we generally do from minus pi to pi, and it wouldn't make any difference. It wouldn't make any difference because we would just have a representation of some function between minus pi and 0, but that wouldn't matter because even if we were to try and determine values between 0 and pi, we would still get the representation of the function between 0 and pi. So the answer to the question is, what do we do? How do we write a Fourier series for a half-range series that's in that we are only given a function between 0 and pi? Well, what we do is that we literally make up something between minus pi and 0, and then we write the Fourier series as we normally do between minus pi and pi, and we just use that series as it is because it does give us the representation. So the question now is, what do we put between minus pi and 0? We can't put anything, but we saw in the previous video where we spoke about even and odd functions. So if we were to identify if a function is even and odd or odd, then we can literally simplify a lot of our work in determining the Fourier series. So the easiest thing to do when we have a half-range series is to either choose whether we want an even function or an odd function, and we write the Fourier series for whatever function we assume between minus pi and 0, and we just continue in that manner. So we can firstly assume, the first assumption is that we can assume an even function between x is between minus pi and 0. So if we assume an even function between minus pi and 0, then what happens is we assume that we have this kind of converse function. We remember that an even function is symmetrical about the y-axis. So if we put a mirror on the y-axis, we should see something on either side. So we also remember about an even function is that it has only cos terms because Bn is equal to 0. So then we'll have Bn equal to 0, and it will contain only cos terms. So that's the one thing that we can do. The other thing that we can do is we can assume an odd function. So if we were to assume an odd function between minus pi and 0, it would literally just be, we would be assuming that there is a symmetry about the point of origin. So if something is symmetrical about the point of origin, then what we're assuming is that we have this diagonal line, and it's symmetrical kind of about that diagonal line. So now what would it look like if it was an odd function? We would assume that the function would look something like that. Okay, so we would assume that this is our function if it was an odd function. So in that instance, an would equal to 0. So we would assume an odd function between x is between minus pi and 0. That would mean that an would equal to 0, and then we would have only sine terms. So let's just do this as an example quickly. So let's just say now we choose that there is an even function. We are choosing to say that there is an even function between minus pi and 0. So that's the function that we are assuming. So in the last video, we looked at what the Fourier series equations become when we actually do this. So a naught would be the integral from 0 to pi of 2 over pi of f of x dx. So that's 2 over pi between 0 and pi of 2x dx. And we have done all these kinds of integrals in a lot of detail in the previous examples. So if we do this, we find that it becomes 2 pi. So a naught is equal to 2 pi. And then we also remember that bn is equal to 0, since it's an even function that we have chosen, and it has only cos terms, the Fourier series. So we only need to determine an. And an, if you would recall from the last video when we looked at even and odd functions, it was 2 over pi, integral from 0 to pi of 2x cos x. And we've evaluated this integral in the previous videos. So you can go and look at the previous videos to see how we've did this entire things, but we need to use integration by parts to determine this. So I'm not going to redo this this entire example again. It's in the previous video if you'd like to go and look at it. But anyway, we see that an is equal to minus 8 pi over, minus 8 over pi n squared. And this is only for odd numbers. So for even numbers, an is equal to 0. So what does the Fourier series look like once we substitute all of these things? So f of x will equal to pi. Remember, it's a naught over 2. So the first, if you can just write the Fourier series quickly, it's a naught over 2 plus the sum of n starting from 1 to infinity of an cos nx plus bn sine nx So we said bn is equal to 0 since it's an even function, and we have only cos terms. So a naught over 2, so we have 2 pi over 2, so that just gives us pi. And then the remainder is minus, and then an was minus 8 over pi n squared, so we can take out 8 over pi as a common factor. So we have 8 over pi, and then we just write the cos terms. So we have cos x, and remember we have 1 over n squared, so it's only valid for odd numbers as well. So we have 1, then the next number is 3, next odd number. So we have plus 1 over n squared, so it's 1 over 9, cos 3x, and then the next odd number is 5. So we have 1 over 5 squared, so that's 1 over 25. And then we have cos 5x, and so on. So this is what the Fourier series looks like for this half-range series, and we have chosen it specifically to be this way. So we have just made up something. We have just chosen to say that there is a even function between minus pi and 0, and we've written the Fourier series for this entire thing between minus pi and pi. So it's fine, it's okay to do this because we still have a representation between 0 and pi, which is really what we are interested in. We could have also did the same thing, and we could have assumed an odd function instead, and we would have a Fourier series with only sine terms. We could also choose neither. In that case, we would have both cos and sine terms, and we would have to evaluate both an and bn. But it's generally easier to just assume an even or odd function, so we can simplify our work in that manner. Okay.
So in this video series thus far, what we've done is that we have written the Fourier series for periodic functions that had a period of 2 pi. In fact, what we've done is that we have derived expressions for the Fourier coefficients a0, an, and bn, and all of these coefficients are only valid for a period of 2 pi. They have only been derived for this specific period. However, in reality, we have functions that have many different kinds of period. It's not guaranteed that the period of the function that we're considering is going to be 2 pi. So we have to now modify our work, modify the Fourier series, and modify these coefficients such that they can be applicable for any kind of period. So we can just consider some kind of periodic function. So it can look like something going through a cycle and repeating itself. So we said that the period is basically when the function starts to go through the same cycle again. So we'll just identify this point, and then we can see it goes through a cycle and then starts to repeat itself at a certain point later. So we could say in general that the distance between these 2 points is some kind of general period t, okay? So the first thing that we're going to do to try and modify this work is we're going to convert our axis, okay? We're going to change the independent variable. So previously the independent variable was x. So now we're going to change our independent variable to be t. So that means that y is now f of t. So let me just write down what we're doing. What we're doing is we're going to convert x to t, right? So why are we doing this? Well, we're doing this because we know the period is 2 pi, and we now want to represent t in terms of this 2 pi. So we're changing t to 2 pi. We need to convert we have to convert to be t to be in terms of 2 pi. So the way we do that is the first step is to change x from t, and we'll see just now where all of this is going. So now that we have changed x to t, and this whole thing is in terms of t, we can think about the period as being the time taken to complete one cycle, because this is now time on the x-axis. So I'll repeat once more that the period t is now the time taken for it to complete this cycle. So the period is this variable t, and what it is the time taken to complete one cycle. So there's our one cycle, and there's our time taken. So that's what the period is. So we can just give it a number, right? We can say that maybe it took 2 seconds, right? So our period is 2 seconds. It took 2 seconds to complete a cycle. So now what we want to consider is what happens when we invert this, right? So what happens when we invert this? So what we're now considering is the number of cycles in 1 second. So previously for the period, we have time taken to complete one cycle. So how many cycles are we completing in 1 second. So this is now what we're considering is the inverse of the period, right? So that is actually called the frequency. And it's the number of cycles divided by 1 second, and it's 1 over the period. And if we were to calculate it, we just gave the period a number. We said 2 seconds, so it's 1 over 2, and that's a half. Okay? So what we're saying is that we're completing half a cycle in 1 second. So this number of cycles in 1 second, it's actually the unit hertz. So this is 0.5 hertz. So hertz is just the unit given to cycles per second. So the next thing that we're going to do is we're going to say, okay, because what we're doing now is we need to somehow relate this period to 2 pi. Everything needs to be in terms of 2 pi. So the next thing that we're going to do is ask ourselves, where do we see 2 pi and where does pi come up all the times? Well, it comes up all the time when we're considering angles. Remember that we express angles to be in terms of radians. And we said that, okay, we have pi radians, 2 pi radians, and all of these things. So that's where the period comes up. That's where we have 2 pi. So we now need to link this period to be in terms of angles, to be in terms of radians. So what have angles? So what has angles is a circle. So we can create an analogy here. If we think about it, we have a start point and we proceed and then we come back to our start point. So that is kind of like moving along a circle. Okay, that's a poorly drawn circle, but you get the idea. So we have a start point and we move, okay? So in the same way we have our cycle, we are now halfway along the cycle, we're halfway along the circle, and then we go back to where we started. So moving along this cycle is like moving along this circle. So this is now somehow talking to our 2 pi and our period and all of these things. So we need to bring in this period somehow into this concept of this circle, right? So we need to take 2 pi, and what we're saying is we have our start point along the cycle and we end up back at our start point. So moving along one cycle is like moving through this one revolution of this circle. And one revolution of this circle is 2 pi radians, okay? So in other words, to complete this one revolution, to complete this 2 pi radians, it takes 2 seconds. So this is what this period is. So we associate this 2 pi with this period. So this period is the time taken to complete this revolution of the circle. So that's the analogy at this point. So we could also say, okay, here is our start point and we move a distance, maybe t1 along this cycle, right? So we are now at this point and this is t1 units after our starting point. So that would be the equivalent to moving theta 1 radians along this circle, okay? So that's theta 1 radians, that's t1 after our start point. So that is this whole thing. So we create a new concept at this stage, or we rather define a new quantity, right? So this new quantity that we're looking at is, okay, so the revolutions, so one revolution is 2 pi radians. So how long did it take to complete this revolution? So it took the period t, so that's the time taken. So if you remember what speed is, in general, speed is equal to distance over time. So this 2 pi radians is kind of our distance traveled in terms of the angle and this time taken in this period. So what we have created is some kind of speed, or rather some kind of velocity of the amount of time it took to move around that circle. So that is given a name, specifically the angular velocity. So that's the angular velocity. So with this angular velocity, we're saying that this is the speed it takes. So this is how the speed will move
when it's going from its start to its finish around this entire cycle. So if you think about t1 and t21 again, so we said that this angular velocity is a constant, right? It's 2 pi over t, so it's a constant. So we said theta 1 is actually this 2 pi, so theta is the distance traveled. So instead of saying 2 pi, we've said some theta 1 distance later. And this time taken, it's equivalent. So we move along this, we move this t1 time later, and that's equivalent to this theta 1. So if 2 pi over t is a constant, it also must mean that it's equal to theta 1 over t1. Or not just theta 1 over t1, but rather theta over t in general. So that's an important point, right? So what we're actually saying is that this unit time, so a unit time along our periodic function, is actually equal to the angle over the angular velocity. Okay, so in the same way, this angle is equal to this angular frequency times this time. So we're writing now the Fourier series in terms of the angle, right? So that is what we are writing the Fourier series in terms of, okay? So this now is actually equal to this angular velocity multiplied by time. And we know that this angular velocity is equal to 2 pi over t. So if we substitute that in, we get 2 pi t divided by this capital letter T, this period. So this is the key thing now. So this is what we're actually considering. So this is now the conversion. We have established some kind of relationship between 2 pi and t and small letter t and all of these things. So we have created now some kind, by using the circle as an analogy, we have linked all of these variables. We have linked this 2 pi and this period and all of these things. So if we now write this Fourier series, so this f of t, so this is our y value. And if we just remember what the Fourier series is, it's a naught over 2, then plus this sum where n starts from 1 and then goes to infinity of an cos. And now we're considering theta, okay? So instead of x, it's now theta. Because we said that we have this circle, and in this circle, we have our different variables. And since it's moving along this radial distance, that radial distance, the angle is actually x, okay? So we have linked that with t. So instead of theta, we can now replace that with 2 pi t over capital T. So we can write this as 2 pi n t divided by t. And we can do the same here. We have 2 pi n t divided by t. Okay, so this is our Fourier series in terms of our new variables for any period t. So the question is, what does our Fourier constants now become? How do we write our Fourier constants? If we just remember what a naught is, a naught we said was 1 over pi, integral from minus pi to pi. Remember our period is 2 pi. And we said f of x dx. So now we replace this with t and all of these things. So just a quick thing. Remember that our period is 2 pi. So we can just write 2 pi here. And remember that that's the period that we had previously considered. And we have to cancel out this 2. So we can put 2 in the numerator. So it's 2 over 2 pi. It's the same thing. So it's essentially the 2 over the period. So if we now generalize this to our new variables, we'll have a naught and we have 2 divided by our period. So that's t. And now we have our integral. So instead of minus pi to pi, we could integrate from either 0 to t. So this is our new period. So t is our period. Or we could integrate, as we had done here, halfway between each of these things. So minus t over 2 to t over 2, as long as this length is the period t. And then we have f of t dt. So that's a naught. For an, if we remember what it was 1 over pi, and integral from minus pi to pi of f of x cos nx dx. So in the same way, this 1 over pi is the same as writing 2 over 2 pi. So we have now, in terms of our new variables, 2 over t integrated from minus t over 2 to t over 2 of f of t cos, now not cos nx, but remember what we said earlier is that we now have cos of theta n, right? So we have 2 pi nt all over t. So that's what we're going to put in. 2 pi nt all over t and dt. And in the same way, we have bn. So bn will be 2 over t, the integral from minus t over 2 to t over 2, f of t sine 2 pi nt all over capital T dt. So we can just illustrate our new variables using a basic example. So we have done this example several times in different ways throughout the course of our work. So what we'll just have is some kind of function. So we have t, and here we have f of t. And then we have maybe minus 2, minus 1, 1, and 2, okay? So we can say maybe from minus 2 to 1, we have function value being 0, and then from minus 1 to 0, maybe it takes on the value of 1, and then it carries on from minus 1 to 1 with the same y value, and then drops back down to 0. So this is the periodic function, and this y value is 1. So let's write our Fourier series for this kind of function. So the first thing that we see is our period. So what is our period? We can see that our period is basically when the function starts to repeat itself. So it starts to repeat itself after 4 seconds. Okay, so it would take on this value again at this point here, and it'll carry on like that. So from minus 2, we have 1, 2, 3, 4. So our period is 4 seconds. Okay. So now we can proceed with our work. We determine a naught, and a naught, if you remember what it was, we just wrote it, was 2 over t, integral from minus t over 2 to t over 2, f of t dt. So our period was 4, that's what we have just established. So we have 2 over 4, integral from minus t over 2 to t over 2. So t is 4, so we have minus 4 over 2. So we're integrating from basically minus 2 to positive 2. And then f of t is basically, we'll have to split this up. So it's going to be, his function is 0, then it's going to be 1, etc., etc. So we're not going to waste time integrating this 0 here and this 0 here. So we're just going to integrate from minus 1 to 1 of the function value 1 dt. So it's going to be 0, integral of 0 is just 0, so, and then it's going to be 1 here and then 0 again. So it's just integrating from minus 1 to 1 of 0. So we get a half, and just integrating t from minus 1 to 1. So that will be a half into 1, and then we have a minus and a minus, so that's going to give us a plus. So 2 times a half is just going to be 1. So that's what an is equal to, sorry, a naught. So a naught is equal to 1. Now with an, we can just write it again. So we said that's 2 over t, integral from minus t over 2 to t over 2, and now it's f of t cos of 2n pi t all over capital T. So t is equal to 4. We're going to substitute it there, and we're going to substitute it there as well. So we have a half. And f of t is 1. So that's 1. So we're not going to waste time with that. So we're just going to integrate this thing directly. So we're going to have sine, okay? And we have 2 over 4, so that's a half. So we have basically pi over 2 essentially, right? So we're going to have sine of n pi over 2, and then we're going to have this t. And then we're going to have to divide this by what is in front here. So it's going to be n times pi over 2. And this is now going to be integrated from t over 2, that's 4 over 2, and carries on like that. But we know for a fact that okay, the function is 0 in these regions here. So we're actually just integrating from minus 1 to 1. So proceeding in this manner, what we're going to get is we're going to substitute all of these things in. We have a half into sine we're going to substitute t is equal to 1, so we're just going to get n pi over 2. And we have to remember here that sine of minus x is equal to minus sine x. So when we put in this minus 1 here, we're going to have sine of minus n pi over 2. So we're going to bring a minus in the front. However, there's already going to be a minus since we are integrating with respect to this lower boundary. So this minus in front now, with this minus, because we're integrating, is going to give us a plus. Plus sine n pi over 2. And all of this is divided by n times pi over 2. So we have 1 plus 1, so that gives us 2. So we're going to bring out this 2 in front. And now we have another 2 here, okay? So what's going to happen is that this 1 plus 1 gives us 2. That's going to cancel off with this 2. And then we take this 2 to the top, and we're just going to be left with 2. 2 sine n pi over 2. Okay, let's also not forget that we have to divide by this n pi. So sine of pi over 2, we need to look at some multiples here. So we have done this in the previous video, so we can just have a look at it quickly. So we have our function carry on like that. So that's pi over 2. This is 3 pi over 2. That is 5 pi over 2. So these are the x values, and that's pi, and that's 2 pi, etc. Seven pi over 2, and so on. Okay. So the first thing we see is that if we substitute in even numbers of n, we're going to have 2. So 2 times 2 divided by 2 gives us 1. So we just have sine of pi, and sine of pi is 0. If we substitute in 4, we're going to have 4 over 2. That's 2 pi. So 2 pi is also going to give us 0. So for even numbers, what this means is that an is going to equal to 0. Now let's look at odd numbers. So we have 1, 3, 5, 7, 9, etc. So if we substitute in 1, okay,
So if n is equal to 1, we have sine of pi over 2. So if it's pi over 2, it's a positive number, so we just have 1. So this an is going to take on the value of 2 over n pi. If we substitute 3, we have 3 pi over 2. 3 pi over 2, we're going to get minus 1. Okay, so we have minus 1. So this value an is going to take on the value minus 2 over n pi. We substitute in 5 pi over 2, we see we have a positive number, 2 over n pi. And it's going to be minus again. So every alternate odd number is negative. That's what we were saying. So what about Bn? Okay, so Bn is going to equal to 0. Why is Bn going to equal to 0? Because this function that we're considering is an even function. We said in the previous video that if it's an even function symmetrical about the y-axis, the Fourier series will only have cos terms. So that means that Bn is equal to 0. Okay, so we are done. We can just write our Fourier series now that we have all of this information. So we will write f of t is equal to a naught. A naught is 1. A naught was 1. So that's 1 over 2. And now we have our constant, so we can just bring it out. So that's 2 over pi. So that's a constant. We can just bring it out, as we had done in the previous videos. And now we can write whatever is left. So we have cos. We substitute in n is equal to 1. So we have 1 over n, so that's 1 over 1. There's 1 in front. And our first constant is, remember, it's 2n pi t. 2n pi t divided by t. So essentially n is equal to 1 here. So we just have, and remember that we have t is equal to 4. So we have half. So 2 over 4 is half. We can just write the half here. Or let's just write it like this. So we have 2 in the denominator. And then we have n pi t. So we have just pi t. Then the second term is going to be negative. Remember, it's alternating. And we have 1 over n. So that's 1 over 3. And now we have cos. And 2n pi over t, so we said 2 over 4, so the denominator is 2, it's 1 over 2. And n is now 3, so it's 3 pi t. And it carries on like that. So the next term will be plus 1 over 5 cos of 5 pi t all over 2, and so on. So this is how we would write our Fourier series. So what we've done is that we have generalized our Fourier series to be in terms of different variables such that it can now be extended to any kind of new period t. So the important thing to remember is this new relations for this Fourier constant. So that is the main thing. Everything is exactly the same. We are still doing this work in this same manner. The only difference is now we're working in terms of 2 pi nt over some kind of general period t. So thank you very much.